So, we're diving into some source material today that literally rewired how we understand the universe. Now, I know when a lot of us hear the name Albert Einstein, our brains immediately go to, huge chalkboards full of dry, intimidating math. But we're going to reframe that completely today. We're not just looking at equations here. We're looking at a radical, mind-bending disruption of reality itself. Think about it. For 2 solid centuries, the scientific world was totally locked into this neat, predictable clockwork universe built primarily by Isaac Newton. But then, the early 20th century rolls around and Einstein just shatters that clock. He completely superseded 200 years of established science and fundamentally changed the fabric of reality as we know it.
To really grasp how disruptive this was, I want you to ask yourself a question that absolutely defies all common sense. What if time wasn't ticking at the same rate for everyone? Seriously, imagine if a second for you is not the same length as a second for me. In our everyday lives, time feels totally absolute, right? A minute on a moving train feels exactly the same as a minute standing still on the platform. But the material we're breaking down today proves that our everyday common sense, it's basically an illusion. And this totally counterintuitive idea is our gateway right into the heart of relativity.
Okay, Act 1, 2 theories, 1 revolution.
Let's clear up a massive misconception right out of the gate. When people casually drop the phrase the theory of relativity, they usually assume it's just one big idea. But it's actually 2 completely distinct theories, and they're separated by a full decade of absolutely grueling work. First up, we have special relativity, which dropped in 1905. This covers physical phenomena, but strictly, and this is key, strictly in the absence of gravity. It's basically the rule book for a completely gravity-free arena. Then, fast forward 10 years to 1915, and Einstein publishes general relativity. This is the big one where he finally tackles the universe on a massive, cosmological scale, explaining the actual law of gravitation and how it interacts with the forces of nature. So we're really looking at 2 halves of one gigantic scientific revolution.
But before we can even begin to unpack either of those theories, we have to talk about the absolute bedrock concept that ties them both together, space-time. Now, before Einstein, space was just treated like this empty 3D stage, and time was this totally separate invisible clock just ticking away in the background. But relativity introduced this wild 4-dimensional unified entity. It means space and time are literally woven together into a single fabric. You literally cannot move through space without altering how you move through time. It's a package deal. And this one single concept is what fundamentally broke classical mechanics.
Moving on to Act 2, special relativity, space and time.
So, stepping into the incredibly bizarre world of Einstein's 1905 theory, we actually have to ignore gravity completely. In this arena, light rules everything. I want you to put yourself in the shoes of a logical detective for a second. Einstein built special relativity on 2 postulates that, if you were a classical physicist, seemed completely contradictory. Postulate 1, the laws of physics are exactly the same for all observers in any inertial frame of reference, which just means if you're moving at a constant speed, the rules of the game don't change. Postulate 2, the speed of light in a vacuum is exactly the same for all observers, no matter how fast they are moving or how fast the light source is moving. And that is wild, because in classical physics, if you're running toward a beam of light, it should mathematically appear to approach you faster. But Einstein said, nope, the speed of light absolutely never changes for anyone, ever.
Now, if the speed of light is completely absolute, that means space and time must be flexible, and that leads us to some truly mind-bending consequences. First, we get the relativity of simultaneity. This means 2 events that happen at the exact same time for one observer might happen at completely different times for somebody else who's moving. Then there's time dilation. This literally means moving clocks are measured to tick slower than a stationary clock. It's real. And length contraction. Objects physically shorten in the direction they're moving. Finally, it establishes a universal speed limit. Absolutely no physical object, message, or field line can ever travel faster than the speed of light in a vacuum, period.
And, of course, probably the most famous consequence of this super flexible spacetime is an equation you've definitely seen. E equals mc squared. It tells us that energy and mass are fundamentally equivalent. They are transmutable. Mass can literally become energy, and energy can become mass. This specific realization was an absolute game changer. It vastly improved our understanding of elementary particles and their fundamental interactions, and directly ushered in the nuclear age.
Now look, if I just walked up to you and said that objects physically shrink and clocks slow down when they move fast, you'd probably think I was completely out of my mind. And honestly, that's exactly what you should be thinking right now. How do we actually know these wild claims are true? Let's adopt the mindset of those early 20th century skeptics for a minute. Where is the actual hard proof?
Which brings us to Act 3, proving the impossible.
It's so important to realize Einstein didn't just casually guess these ideas. He used incredibly rigorous deductive reasoning based on hard evidence. Just listen to how he actually categorized his own work. He called relativity a principal theory. He explicitly stated that principal theories start not from speculative constructs or imagined mechanisms, but from well-established empirical facts and observed regularities in nature. He wasn't some wizard pulling magical ideas out of thin air. He was a brilliant analytical genius working backward from experimental data, figuring out the absolute logical constraints that any physical process had to obey.
Let's actually trace that timeline of validation. Prior to Einstein, the scientific consensus was that light traveled through this invisible, universal medium called the luminiferous ether. But in 1887, the Michelson-Morley experiment tried to detect this ether wind and found absolutely nothing, zilch. They proved that the round-trip travel time for light is totally independent of direction. Then, jumped in 1932, the Kennedy-Thorndike experiment goes even further, proving the magnitude of the speed of light is the same across all inertial reference frames. And finally, the nail in the coffin, 1938, the Ives-Stilwell experiment looked at moving atomic clocks and observed the exact Lorentz factor correction that Einstein had predicted. They confirmed definitively that time dilation was real. Experiment by experiment, the old Newtonian paradigm was completely dismantled.
All right, let's jump to Act 4, General Relativity, Curved Spacetime.
So, by the 1920s, special relativity was becoming widely accepted, but there was still a massive, glaring puzzle piece missing from the board: gravity. The big breakthrough came with what's called the equivalence principle. Einstein had this realization that the state of accelerated motion and the state of being at rest in a gravitational field, like say you just standing on the surface of the Earth right now, are physically identical. This is huge. It means that an object in free fall isn't actually being pulled by some invisible force of gravity like Newton thought. Instead, free fall is just inertial motion. Objects move that way simply because the space-time around them is warped and curved by mass and energy. This was a total contradiction of classical mechanics, where inertially moving objects just can't accelerate with respect to each other. And because of this, general relativity dictates the macroscopic universe in ways that are just truly staggering. The Einstein field equations predict some absolutely wild cosmic phenomena. We get gravitational time dilation, which means clocks literally run slower the deeper they are in a gravitational well. It explains the weird precession of Mercury's orbit, which Newton's math just couldn't quite figure out. We can actually see light rays physically bending around massive objects in space. We see rotating masses dragging the actual fabric of space-time along with them, and on the absolute grandest scale possible, it accommodates the expansion of the entire universe. I mean, it predicted neutron stars, gravitational waves, and black holes decades before we even had the technology to actually observe them.
Which brings us to our final section, Act 5, Relativity in your pocket. Now you might be sitting there thinking, okay, this is super fascinating if you're an astronomer, but what on earth does curved space-time and time dilation have to do with me? Well, relativity is actually a highly practical, everyday engineering concern. Just look at your smartphone. Our global positioning systems, like GPS or GLONASS, rely entirely on a network of satellites orbiting the Earth. Because those satellites are zipping around incredibly fast relative to us on the ground, special relativity says their onboard clocks should tick slower. But because they're also much further away from Earth's mass, general relativity steps in and says gravitational time dilation should make those exact same clocks tick faster. It's a cosmic tug-of-war. And if our engineers didn't use Einstein's specific equations to calculate and adjust for those competing relativistic effects, satellite synchronization would fail completely, and that GPS in your pocket would be absolutely useless in a matter of minutes. And the same exact principles apply to things like electron microscopes and particle accelerators. They literally just wouldn't work.
So, from predicting the behavior of supermassive black holes to literally just making sure you don't get lost on your way to a new coffee shop, relativity completely rewrote the rules of reality. It proves beyond a shadow of a doubt that our universe is far stranger and far more deeply connected than our basic everyday senses suggest. So I'm going to leave you with this one thought. If relativity could shatter a 200-year-old illusion of classical mechanics just to make your everyday technology function, what universally accepted established fact of our reality right now is just sitting there waiting for the next Einstein to completely break it? Thanks for diving into this explainer with me, and definitely keep questioning the reality around you.